Just a sec. Yes, please go ahead.
So, thanks everybody for joining. My name is Florian Renneke. I'm from Infineon in Munich. And today I want to show you this MOSAIC framework that we recently developed together with our CISC colleagues, and want to do a small deep dive. So basically we have three parts. First, motivation. Then next, we will do the deep dive into real coding, basically. You don't have to do anything on your side now, but later on you can try it on your on your PC. However, it would be great if we do it a little bit more interactive. I have small quizzes in there, so to see if you get what I'm trying to say. And last but not least, just to show you this small demonstrator, you can then explore it on your own later on. This as the last point. So let's start with the first one. So the motivation. And one second. So like 3 years ago, I attended a boot camp in Villa about back, and I was not really, let's say, familiar with the generators. So I was kind of new also to Python, and then I was confronted with this back2 framework. And for me, at least, it was like this huge pile of code that I could not really understand at first. It was quite, let's say a big mountain. And just maybe to get to know you a little better, a few questions. So who of you is familiar with back? So we have like 5, 6, 7 people here. Three of 7. Okay. Who's familiar with the line? So it's another framework that the Texas University did. Okay. Magical. Also not. No one. Okay. What about this open FastDoc? I heard it yesterday, and I just Googled it yesterday. Okay, also none of you. Okay, and who has worked on a generator collaboratively with other ones? Okay, 1, 2. Okay, that's good. So you may. So I tried already to picture this problem, right? You stand there and you have maybe all of these different frameworks and you don't know exactly where to start, how to install them. And especially me, I got the task at Infineon to get this back up and running in our design system. And it was a really challenging task. And later on, then there was back3. And I tried to set up back3. There's some stuff that had to be compiled. It was really difficult, and I wouldn't say that I really succeeded. So the problem that I'm seeing here is that the entry point is a little bit too high for all of these frameworks and for these tools. We have different technology setups for all of them. We have the frameworks itself, the generators, they have written in their own style. So the question is, where to begin, how to install and how to reuse what you have already done. And here we want to bring in this MOSAIC, which sits on top of all of these different frameworks, basically. We want to give it a common interface so that later on, when you maybe program something with back, it doesn't mean that you have to throw it away if you switch to something else or want to try out something else. That it's like a plug and play system. If you support this interface, everybody can reuse it. So it could be something like this. So on the bottom, we have our MOSAIC framework. On the top, all of these different frameworks that may support the MOSAIC. And on top of it, you have the user generators that then they can just pick what they need. This is kind of the vision. So the MOSAIC framework is there that we want to share and reuse our work. So your benefits, basically, if you are compatible with the MOSAIC framework, means that you have, or the users of your tool have a low and common entry point. So each of these generators or also frameworks can be started and fed with parameters in the same way. So this is, I think, very nice selling point. The next one would be the installation should be as simple as pip install. I put it in quotation marks because, we don't want to enforce now pip. It's just one suggestion that may work. And for the demonstrator, I used Python packages to package everything. And this is true for all parts. So for the user generator, for the MOSAIC framework itself, and maybe other tools that maybe back later on comes in, we just do a pip install and then you can use back inside of it. So this is the idea. And of course, we want to foster reuse. This is like this buzzword that Christoph Sandner already mentioned. Because we have this common API, you can just reuse everything. And the framework comes with some very nice parameter handling, meaning passing around parameters from one generator to another is always kind of a tedious task, and each framework is handling this in its own way. Here we propose some standard parameter handling that should cover everything that you need. And last but not least, because we separate currently the initialization, so the declaration of parameters and stuff like that, from the execution of the task, we can do checks before running the generator, like checking if the tools are available, if the PDK has the correct views, if the generator corrects the correct parameters as an input, are the parameters valid? All of these checks you will see later on can be done before execution, so that you don't run a simulation for 2 hours and then suddenly, error, you forgot to mention some input specification. Exactly. So this is just now a teaser. I don't want to go into too much detail, but what you can see here is a very minimalistic example. So you import from MOSAIC, you create this class. We just have a dummy adder class here that inherits from a task. Everything is a task. So basically a generator would be a task. Yeah, exactly. And inside of this task or generator, you can specify first the parameters, just like that. So these, you can just define them up front. And then each task has a run method where you then execute whatever you want to execute. And last but not least, so this would be kind of your generator, so to say. And then when you want to call this generator, really run this top level, you can then just create this builder, add this class as a root, define some parameters, build an instance out of it, and run it. So we will go in much more detail about each of these points in the next section. But maybe before I give you some more insights, are there any questions so far? So this is kind of the motivation part. The next part would be the workshop. And then we go through all of these individual steps. Okay. On the
it looks like we need a wrapper for translating generator A to generator B, and those generators are written in different languages, Python, C++, or then
yeah. So here, so this framework is now based on Python, basically. So this interface to your custom generator has to be a Python class in that structure that we have seen. But actually at Infineon, for example, we have also a layout generator, in-house layout generator that is written in C++ and JavaScript. And you can just provide a Python interface for it that then translates basically these MOSAIC input parameters to the framework specific stuff. Exactly. So this would be required. Yes. I'm not sure if the audience can hear the question, so maybe next one I will repeat. So the question was about this interface between different generators written in different target languages.
I had a question.
Yeah.
For example, if we want to use Magic, I don't know if you can hear me well.
Yes, yes.
If we want to use Magic with MOSAIC, we have to create a class that inherits from task and somehow communicate with Magic through that class. I'm right?
Okay, yeah. So this goes maybe into a part that I will explain later, because this I would see maybe as a tool, and we have a special concept for tools. And come back to me if you still have the questions in the question in the end. I hope it.
Yeah, comes. Yeah. Perfect. Review it later.
Perfect. So I guess are there any other questions so far? Otherwise, I will just proceed and I will try to make you an expert. So basically I have this progress bar on top and we will try to fill it up. So this is kind of the overview of the MOSAIC and all the, I would say, major topics that the MOSAIC framework addresses. So first we have the tasks. First, tasks is the fundamental thing. We have the parameters, how to handle those. Then what you asked about the tools. So how do we handle tools inside of the MOSAIC framework? Then we have the PDK. So we need some technology information. So how do we access those? Then we have assets. So basically assets are things that you deliver with your generator that are kind of read-only, like schematic templates or stuff like that. Then we have some powerful caching mechanism inside. And last but not least, of course, a common logging system so that not all logs are spreaded over the place. And I propose to start with the tasks at first. So who of you is familiar with Python? So almost everybody. So you will, it will be boring maybe for you, the next two slides. But who of you is familiar with the data class in Python? Okay, one. Okay, then it's maybe something new. Okay, so because this concept is quite important to understand. So a data class is basically a class that just contains some data. That's why it's called a data class. And in Python, you can just annotate it, for example, like that. And you can just write X and have some type annotation, for example. So this means this is an integer. And you can also then define some default values. And what this annotation now does is that in the background, when you now create an instance of it, the annotation actually by itself will create a constructor for you, and also some additional operators like equality and stuff like that. So you don't have to write all of this boiler code yourself. Everything will be auto-generated here. So basically, if you then try to instantiate it, you see, yeah, here we already have a constructor built in. And now the very important thing here is that these parameters basically that you define on the class level, when you create an instance, it will be, it will become an object member. So these are not class members anymore. Inside of this object, we have really object members. And this concept is also used in the MOSAIC framework to define the parameters. So this, we have then less boiler code for setting up because we don't have to write a constructor or something like that by ourselves. This is all done by the framework. And we are using this concept, of course. So now, little quiz. We have here now two codes. It's almost exactly the same. We have a class, example class. We create an instance. So the default value of x is 1. We now say from the class dot x is equal to 5. And we print the value from the instance member a.x. So now the question is, what will be printed here? Exactly. On the left side, now here we have annotated it with a data class. That's the only difference. Can you guess what's now the output?
I think 1.
Yes. Why?
Because the data class, it's like priority. I think in the
Data class is the priority. Yes, so you have now a data class, and when you create now an instance, this x will be saved as an object inside of A, right? So when you now change the x from the example here from the class,
and not the object.
Exactly, exactly. We are changing the class, not the object. Exactly. So here the output would be 1. Okay, so this is really the concept between these class members become object members. Okay, that was the Python primer. And now we can start to have a look at an example task from before. So as you have seen before, we have here this adder class, and we define some task parameters. It's the same thing with the data classes here. We have just type annotations. So the MOSAIC framework, so this happens in the task base class, it will handle basically this instantiation of these objects for you. So you just declare whatever you need in here, and later on they will become object members, and therefore you can access them with self dot whatever. Okay, and this run, of course, is then executed when needed only. These ones will be called when you instantiate the class. Okay, so an adder, yeah, it will just sum up x1 and x2. This is quite simple, I would say. So now question to you again. So when we now instantiate or we use this as the root task with parameters 5 and 3, and we run this code, what do you think will be the output? Exactly, 8. And the nice thing here is that later on, we don't have it yet, but we want to have a GUI in the beginning that we can enter maybe parameters in a standard GUI. So because every task offers the same interface, we know all the parameters and depending parameters and whatsoever. We want to provide a small GUI so that you can call tasks in a common way. So even for non-programmers. Yeah, so now let's have a look at a hierarchical example. So you usually don't have just one task and run it. You usually have maybe some optimizer running something, and it goes in a loop and multiple subtasks and so ever. So here, for example, we have now just 2 of those adder tasks that we've just wrote. And we already see here a nice concept, because we want now to feed the output of the first task to the input of the second one. This means now that this input here of I2x1, this is now a calculated parameter. We call it calculated parameter because it's not settable basically from above. It's calculated inside of this run method. So we have now two types of parameters, calculated parameter and a derived parameter, which is the default behavior. So if you say nothing, like we said before, x1 is just some value and you don't set it from above, it will just be visible to the root. So it will go up. And there are a couple of more ways to assign it. I put it in the appendix. You can later on maybe have a look at the tables, but yeah. So this is this concept of parameters, and this is how it looks in code again. So like you have two instances that you create. You just do it here as a class member again. So this is done up front. So you see later on kind of this dependency between different tasks. And this is also a very nice thing that we can then later on use for caching and stuff like that. But never mind. So here we define all the tasks that we want to use. So instance 1 is just add. We don't say anything else. For instance 2, we say now, OK, we want to set x1 as a calculated parameter, so that in the end, in the run, we can just run the first task, just call the run method, and then later on say I2 run, and then pass in this x1 result of the first instance. I hope you can follow.
Hi.
Okay.
Sorry, I'm a little confused. This add, it's a class that inherits from task.
Yes.
Where it comes?
Where it comes from, the task? The task is basically the base class for all tasks. It's part of the MOSAIC framework. And yeah, this add that we had it in the slide before, it's not shown in here. You could have here maybe an include from something, my generator include add.
And add, it's a kind of task.
Exactly. It's another task. Yes.
Perfect.
Exactly.
Thanks.
So just show you, here was our adder class. No, sorry. Here was our adder class. So this is add, and now we have here we are using this add class. And yeah, so I think the next question will be then again simple. So if we now run this task at 3 as a root, we just do it like that. We create this builder object, and then we can define, for example, parameters. We pass in as I1 x1 5, I1 x2 is 3, I2 x2 is 3. So what's the output then? 11, exactly. All right, so conclusion for the tasks. We have the separation of declaration and execution. Meaning we first define the classes, the parameters, other dependencies later on, and then we have a run class, and this is only called once needed. Second, you can run all tasks, all kind of tasks, the same way. You always just use this MOSAIC builder and pass in the root level, and then give the parameters and say run. And last but not least, this of course enables the reuse, which whatever the task may look like, what it does, you always can use it the same way. Okay, questions so far? Yes.
Can you explain again what the root argument is? What
So-
do you usually set in the root?
Yeah?
Yeah.
Okay, so the question is about this root argument. So this is a kind of the root task. So you can imagine you have a tree maybe of tasks, and maybe at the bottom you have some schematic generator. Next to it maybe some layout generator. On top of it you have maybe a design script that then uses the schematic and layout generator, maybe together with some extraction to size the circuit in the loop. And on top, you maybe have the next level of hierarchy. So you build up this tree of tasks. And with this root, you say now, okay, I have maybe a SAR ADC generator. And this class you would put as the top, as the root in here. Okay? Hopes this clear, it. Other questions from the audience? Okay. Let's move over to the next topic, if you're still capable of listening. Maybe we will do a short break. Maybe at tools. Okay. So parameters. Parameters also have a base class. It's now called task parameter. And a task parameter has just a value and a description. That's it. You can extend it, of course. If you maybe just derive from it, you can add additional fields like min, max, maybe some testing grid, whatever you like. But the most important two fields that have to be filled in for the MOSAIC framework to function properly is the value and the description. Additionally, you have also two other functions or methods. You have the task hash function that we'll see later on that is being used for hashing and caching, of course. And the default it just pickles this whole thing. I will explain later. And the last one is a validate callback function that you can specify. At default, it's always kind of a valid value. You can put in as value any type. But if you derive from it, you can override this validate function and introduce some checks like is it really a string? We will see. So yeah, this is an example here for the string, for example. If we want just to define a string parameter now, we could just inherit from task parameter and override this validate function, which is just checking if the self.value, we store a value, is really a string. If not, throw in validation error, and we will see it later on really on top when we want to instantiate everything. But here you have entered the wrong type. And this can, of course, be done then also with min, max. You can extend it as you wish. Exactly. So this is, for example, a string parameter, and you could think of more complicated stuff like OA cell views, where you store maybe some data structure inside of the value. And the nice thing here is now, because it's highly extendable later on in the GUI, you could provide maybe special graphic elements for each of those parameters. Exactly. So this is now another nice feature that we support lambda functions. So we often see that we need maybe some logic behind the default values that we want to use. And here it's a nice thing that you can just say, yeah, task parameter, and you can set it default. It can be a literal value, a Python object, whatever, or a callable. And if it's a callable, then you can then this callable will be executed just before execution, or when you do this checking of the input parameters. So that's, yeah, exactly. So this is the lambda function. So here we just get basically always as an argument the task itself, and we can access everything from inside. For example, here the value of x1 and just append some string. But we could, I mean, in a practical example, it would be, for example, if you want to access some PDK data, which is not available in the beginning, but only when the PDK and all the tools are maybe initialized. So yeah, this is a lambda function. And I mentioned already these checks here. You can, if you are now on the top level, run this check method. And this will now check all of your inputs, all of your parameters, all of the available tools, PDK, whatsoever, and gives you, for example, here a list of all available parameters that you can set. Exactly. Okay, so conclusion for the parameters, you can customize those. You can just write the class, write your own. You have the possibility to validate the parameters with this callback function. Third, you have the support of lambda functions. This is nice. And for example, with this calculated parameter, you have the possibility to control the visibility. So you can hide parameters, make it visible to the outside, make it then overwritable or not, and so on. Okay, questions?
Every class has check function
Every class check?
to run check.
No, this check basically is always run before. So in this example, basically we would have run it okay, here's just one. But if you would run, make a run below, inside of the run method, we always do the check up front. So there's no way around this. Only when you really want to access basically this information, then we will need to call the check method, but it's not mandatory. Okay. So now let's have a look at tools. So in the MOSAIC framework, we have two types of tools. The first one is, we call it now batch tools. So this is kind of the default one. You just run something and you get a result. So for example, you could think of a Spectre as a simulator. You run some simulation and in the end you get a result. This would be a batch tool. But then we also have maybe some IPC tools, which is more interactive. So for example, Virtuoso. If you want to start Virtuoso in the beginning and then do some communication through the skill bridge, for example, and then at the end, maybe we want to close it. This would be then a classical IPC tool. So magical, no, not magical, magic. If I'm not mistaken, it's just a layout viewer, right? So I guess it would then more fit into this batch tool category.
I think Magic will be more than an IPC,
Okay.
so we can communicate with German. Yeah.
Okay. Yeah. Exactly. Okay. So hint magic would be more an IPC tool actually, because we can then communicate with it. Yeah. It's possible.
We have to play with it to be where it goes.
Yeah. Exactly. Yeah. So these two tools, and how do you use those? So imagine you have your class again, and you just use basically, or you want to use Virtuoso, the connection to Virtuoso, you say Virtuoso and do as a type annotation the tool, the class tool that we have seen in the previous slide. And later on, when you now create an instance of it, here you register the tools, basically. So you have this long chain of available tools. And what you're saying here is, okay, whenever a task has something of type Virtuoso, then use this instance. So we create this Virtuoso instance just once, and it will be injected into all tools, all tasks. Right? So that we really initiate this connection to this tool in the beginning. You have the communication with all tasks, they share everything. And then at the end, we will maybe close the connection or close the program or whatever. So this principle of injection is quite nice.
Yes.
The agreement from the audience, that's nice. And maybe it can become a little bit tedious to write all this register and maybe set up a PDK and stuff like that. Therefore, we also provide this with configuration method so that you can basically outsource all of these configuration stuff that is maybe PDK specific, technology specific, company specific, into a separate class. Exactly. So here you have just, for example, you can return the PDK, we will see later on, or just return a list of available tools. So this is the central configuration file. Now, question. So we have here again an example task with one parameter x. Okay, we have some variable that is just type annotated with a string. And in the run, we just print the two values. And now we say here in the create register string hello. What do you think happens now? Because this injection is working for all types, basically. It does not necessarily has to be a tool.
The message will be of type hello, something like that.
No. The message will not be of type hello, something like that.
And 9.
Why 9?
Or the description says what is third and value.
Okay, yeah, this is just a description. But yeah, the default value is 3. We do not do anything with default value. So it will say hello 3, actually.
Post message has this annotation of string.
Yes.
And we register string as string hello. We have this injection.
Exactly.
The message.
Exactly. Because I'll repeat, maybe the audience has not heard it here on the phone. So because we have the message of type string, here we say register. So every time it finds in any task a string as a class member, then replace it, or not replace it, but in the object, it shall become hello. Or hello. Right? So exactly like that. Okay, so conclusion for the tools. We have two types, batch and IPC tools. tools are injected where needed. IPC tools are lifecycle managed objects, actually. So this means that you have this on start callback and this on end callback. So you can do something when this whole thing is being initialized and clean up afterwards. The validity, so I'm not sure if we have seen it here. We have also this callback function inside of the tools, and that they can check, is maybe the virtuoso binary really existing? Does the version match or something like that? So we also have here a validity check. And last but not least, we can outsource this configuration of tools, PDK, whatever, in a separate file. So that we can have maybe a common setup file for the entire company, university, whatever, for one technology. Okay, questions for tools? Otherwise, I would, well, the first questions.
It could be possible that we can compare two generators, like Virtuoso and Lego 2, making the connection and, for example, making an LBS.
In principle, yes.
Yeah.
Yes, we have to then program this and add those two together, yeah. But in principle, I would say, yes, we can. This framework is really generic, right? You can put in there as a task whatever you like. So you can, as you proposed, add magic, whatever you lay out.
So the version of the tool that's available in the specific company or university is placed in the configuration file, right?
Yes, exactly.
So when you check the validity, it's because the person who wrote the task, who wrote the specific task, is expecting a certain version of the tool. So that what the valid checker does is it cross-checks the one that's in the configuration file, which declares the version of the one that exists in the system at the moment, and the one that the person who wrote the task expects. Is that it?
That's a good question. Because I think for tools, we just have basically a tool, and this class tool has this validity checker, and yeah, basically this wrapper, this tool wrapper defines what version it provides. So I would do it maybe like that. So you have to provide this tool wrapper. This tool wrapper supports just a specific version of the tool. So these are really linked together. But they are, again, a Python package, for example. So later on, you can specify that the generator needs a tool wrapper of a certain version. And implicitly, you say, OK, this means I need a specific tool version for this. So we have this 3 points, right? The task specifies dependency on the tool wrapper, and the tool wrapper checks the compatibility with the version of the tool.
So then the tool wrapper checks that directly with the tool itself.
Yes,
right?
exactly.
To specify the version.
Exactly. So basically, you would have to write a new tool wrapper if maybe a different version needs to be supported and it's incompatible. Then you need to update the tool wrapper.
I see.
Yeah.
I think that would be nice that I think that with an extension, we make the MOSAIC, we have some kind of support of Docker. When we use a tool, we can create a Docker instance that downloads the specific version, and we don't have the kind of problems that my teammate talks about.
So you're saying that you want to introduce a Docker?
Yeah.
Basically, in the tool wrapper, let it automatically then uses a specific Docker.
Create another kind of tool. It's the batch, the IPC, and the Docker tool.
A Docker tool even, okay.
The Docker tool will be inherited from IPC, so we can use it in the same way.
Yeah.
But we have a startup, maybe a startup thing that downloads image that there exists the image of the tool, and you can use it.
Yeah, this is, I guess, a nice idea, right? So
I think that you're in Infineon don't use Docker.
yes, at Infineon, Docker is kind of a problem maybe, but yeah, I guess we can talk with IT. Yeah. Yeah, but this would be a nice idea, really. So the proposal was not to have batch and IPC, but also a Docker tool, which then automatically downloads the Docker and initiates the connection with the tool within the Docker image. Yeah, nice idea. You're free to work on that. Okay, shall we do a 5 minutes break, or? I think so. So everybody can fill up, and then in 5 minutes we can continue. Okay?
Okay.
Questions in the chat.
Florian, maybe you just turn off the mic in the meantime.
Hey. So. So I guess we can continue slowly if you haven't fallen asleep. So let's start with the PDK. So this is of course very important. Up to now, I would say it's quite generic framework you could use for everything. But the PDK part, this is really, I would say, also essential for the application inside of the, to design some analog IP over. So a PDK is here in the MOSAIC framework a collection of views. So you can have a PDK, for example, the CDS FFmpt PDK, and you have different views. And behind each view, you basically have some configuration file, for example. So if you're familiar with BAC, it could be maybe this tech params.yaml file or something like that. We have also this Python base view, which is also then basically just a file and a class name. And here you can then, for example, programmatically define how the configuration should look like. So these are basically, again, the base classes. You collect them into views. And now on the right side, we have our interface, meaning you would be sitting here in the task. You will define a view wrapper, or you will use a view wrapper to access the information inside of the views. This is really confusing at first, but once you see it, I hope you will understand. So basically for each type of file, you can have a dedicated view wrapper for it to access the information in the file more convenient. So for example, these are just really simple one, a JSON view wrapper. If you have a JSON file, you can just use the JSON view wrapper to read the information in the JSON file. And each of these view has a name and a version. So it can be that a task needs yeah, maybe the view 1 in version 0.1.0. So he will just define it here later on in the view wrapper. And through the MOSAIC framework, it will grab and search for the correct view. Okay. And yeah, this is not used yet, but in principle, you could also then group views together in a library. Okay. So now, how does this access looks like? So here, for example, if we have this Python view wrapper, we again just define this dependency up front. We say, yeah, Python view wrapper, and we say name and version. And here we use this semantic version scheme to actually define what versions, what view versions are compatible with this task. So here X is just a placeholder, so whatever is in there would be sufficient for this tool. And later on in the run, we can just access the information like, yeah, so this Python view wrapper will instantiate whatever is inside of it. And you can, for example, get the TP name, design package name out of this construct. So yeah, here I already said it. We have this standard versioning scheme. It's well, quite nice. And it could be, for example, that we have a view, for example, view 2 is inside of the PDK in different versions. So we have 2 times view 2, but different versions. And maybe different tasks need a view version that is maybe different. So this is how you can then define the dependency. And with this X, for example, it will then, if it finds multiple matches, always take the newest one. But here actually, okay, this is does not fit together, but yeah. Okay, I think this is already everything that you need to know for the PDKs. So the PDK is a collection of views. Basically, there are just files inside of it with a specific name and a version. You access this information through view wrappers. And last but not least, the task and tools, they can depend on specific views. Okay. Questions?
Actually, PDK has more than only views. But if you mean the view is a view or for per instance, for example, one transistor, right?
So here this PDK is a little bit more abstract even, I would say.
Okay. Because actual PDK has also all our rules, even the routing, the spacing, and the antenna rules. Yeah. But okay, for at the beginning, it's enough.
Yeah, and we can think of maybe what else needs to be added here, right? So in general, this is kind of a proposal, and it's in work. And if you have any ideas of what is maybe missing, we can add it. Other questions?
What does this already work with?
So currently I have a demonstrator for a schematic generator. So this is currently how I tested it, basically. So I have a PDK view that maybe defines the available devices inside of the PDK. And maybe some additional information like, how are the CDF parameters, how to kind of mapping tables in between and stuff like that is in there. You can have a look later on. It's all on GitHub. Okay. And let's move over to assets. So this is also quite fast, I guess. As I said in the beginning, assets are read-only static files that you deliver with your generator. And if you use, for example, a Python package, they would be installed with this Python package, for example. So This is also why, for example, here I have this example that I'm using for the schematic generator to render a few files. And I deliver here some template files with it. And I can just do it like that I use this asset class, give an array of files that I want to package with this generator or with this task. And of course, because they are inside of a package, a Python package, you have to know the package name. And this is currently the way you do it. You just pass in the package name and then this relative path to this resource. Exactly. You can access then the files inside of it just by self.templates once.path, for example. And there you get then the full path to these resources. And you can do whatever you would like with them. Yeah, so that's already it. So assets are read-only dependencies. For example, the schematic template. So I use it for the schematic templates, which is an OA library. Chain, this we will see later on. So if we change something on the disk, really, this would then later on invalidate the cache. We will see it later. Assets are also life-cycled. So in the beginning, you can do something, maybe initialize something with this asset, and then later on clean it up again. That is also possible. And they are delivered and packaged with the Python package. Questions to that?
Python library will be an asset.
A Python library will be an asset. You mean like a Python package or?
Yeah, like
this,
for example, Lego 2, it's a Python package.
No, this I wouldn't say because currently at least it's like you have all of these Python packages that you can just install and then just use, and each Python package defines its dependencies inside of the setup.py or pyproject.toml or whatever you use there. So we want to use currently this pip dependency management to resolve those dependencies on other Python packages, not with assets.
Yeah, right. Thanks.
Perfect. Good. Caching. So this is also a very nice thing here because we don't want to do things twice. And I'm not sure if you worked maybe with back or something like that. It often happens that you regenerate the entire layout, whatever, all over again and again and again, and you wait a long of time until you reach the point that is interesting to you. And that's why we now introduce this caching mechanism, and it works something like that. So imagine I already tried to build this picture of tasks in a tree. So imagine you have this top level task A, and it depends on task B and task E, and so on. And it goes down. When we now run it, all of the results of each task will be stored in a database inside of a cache directory. And later on, when we now run it again, we can actually check, because we have the separation of initialization and execution, if the task is actually valid or not, or if the results are still valid. So imagine task C is now invalid. Then it could be that, okay, the MOSAIC framework detects, okay, I have to run task A again, task B again, task C again, but the other ones, the inputs do not change. I can just reuse the results from the cache. So this means now, if you imagine a task A, for example, has some input, some results. This means now that the inputs And currently the source code of the task will go into a hashing algorithm, and it will create a unique hash, meaning if the inputs change, the hash changes. If you change something in the source code, the hash changes. A different hash means the cache is invalid. On the other hand, on the results, if it produces some results and later on you will want to check if the results are still valid. For example, you generated a layout and the user just deleted the layout, so it's not existing anymore. This can be checked here in a callback function, and it can return and say, yeah, okay, the layout is still there or not. And all of this together, you can really say if the result in the cache is still usable or not. So here, how do you use it? You may have seen it already in one example. We also provide this cacheable task base class. It adds a little bit of stuff on the base class task, but you can just inherit from this one instead. And then this task will be cached without anything from you to be done. And what's now been added is this invalidate function that you have to write. So this invalidate function checks basically the results with validity. Okay, so imagine in the first run, it runs through, some result is being returned. In the second run, the invalidate function will be first called to check if the result from the cache, so this basically from the first one will be put in as an argument, if this is still valid. If it's still valid, okay, return true. Otherwise, if it's still valid, return false. If it's not valid, then return true. This is how you use this mechanism. And now question to you, which is a little bit tricky. What will be printed now in the end when we call it 3 times? The cache is in the beginning not available, so he has to execute in the beginning.
What's called?
Invalidate is called when the cache is available. Okay, so this is a good hint. Yeah.
So the first time it will work because there is no cache.
Exactly.
But the second one, the validate because invalidate always return false. No.
Yes.
Invalidate false is.
Invalidate false.
It means that it passed. So we will use the catch.
Yes. So. So how often do we print hello?
Just once.
Just once, exactly.
Huh?
And then 10 times, 10 times. Okay.
Exactly. So in the beginning, we have no cache, so we don't have a result, so we cannot call the invalidate function, right? Meaning it goes through the run, says hello, and returns the result 10. On the second run, because it's stored it now in the cache, it will first invoke the invalidate function to check if the result is valid or if it has been invalidated. And now it's returned false, meaning that the cache is still valid. This wording is maybe a little bit confusing, but it's still valid. meaning that it does not need to execute the run method. It can just reuse the value 10. So meaning, yeah, 2 times 10, because we call 2 times the invalidate function.
So this happens when you make 3 instances of the example.
Yes. Basically, yes. Does not matter in which hierarchy this task is being called. Yeah, because they all use the same cache. You can have multiple runs. Yeah.
So if you have like in the 2 instances of say task A, right? So it's down here and then up there. So
Yeah.
The task A up there, the one down here already ran. Will use the cache results.
Exactly.
I see.
Exactly. So this is also nice, right? Because you don't have to do things twice. If you maybe generated already an OTA with some specs and you use the same OTA on the other side, you can just reuse it. Why do the things twice? Exactly.
And this that's the kind of mechanism that removes the cache if we get out of memory.
Yeah, so currently, as far as I know, it always adds to it. So if you run out of memory, so they are stored on the disk, right? They are not in memory and on the RAM. So they are really on the hard drive. But it will add up, and yeah, I'm not quite sure. I think we don't have a size limit yet. I have to check.
And when we say that the invalidate result is true, the catched result gets removed, so we don't use that. What's basic?
It will be updated basically then.
Updated.
Because then the run will be run again. We get a new result, and this one will be stored.
What if, for example, you have, say, you depend on a current mirror, right? So a task generates a current mirror, and the sizing for the, say, the other current mirror is different because of the way you like declare the task at first, or because its dependencies are different. Then there will be 2 caches for, say, the one current mirror with another side and the other with another, even though they're both the same task, just with different.
Exactly. Exactly. So if the hash changes, so the input parameters have changed, we store it somewhere else, basically, right? Yeah. So different input specs lead to different results, meaning different entries in the cache. Okay, so to conclude here, whenever you say a task can be cached, then just use this cacheable task as a base class. And the task is invalid if the source code changes, if the input parameter changes, or the results are invalid. And last but not least, with this invalidate callback, we can check, or we should write it ourselves and check the validity of the results. Okay. Then very quickly logging, and then we are experts. So with logging, it works like that. So we have, so each task first has its own working directory. So this means when you have, for example, generator a.py here, next to it, you will find a directory, mosaic.work, I call it just like that. And inside of it, you will find generator A. And when you run this one, it will actually do a change dir into this directory. So whatever file you create, whatever will be inside of here. Additionally, you will also see here a log file. So this means each task has its own logger instance. So you can use just this logger instance. It's a typical Python logger. to log anything to this file. And it's actually hierarchically. So meaning if you now have additional subgenerators, we have this directory structure here. And each of them have the log again. And currently it's like that the log entries of those you will also see in here. Right. So on the upper hierarchy, you see everything. And then you can go down if you just are maybe interested in the results of the subgenerator A or whatever. Question?
Sorry. When we talk about the subgenerator, we are talking about the task.
Yes, yes, yes.
So if we use a task near the root, and then we use the same task in the leaves, we will have two different folders that contains the logs of these two different tasks.
Yes,
right?
exactly. So
the same task has two different folders.
Could be, yes.
Because the context.
Yes, it could be. I just have to think what happens if you have now this generator A down here. Then basically this generator A would use those again. And this one, so it looks like this recursive loop. So you would have to break it at some point. But in principle, each sub task will get its own directory. You just have to be sure that you don't cause any recursion. When doing that.
You would have cache for that, though, right? Like you would catch that variable, right? It's invalid to instantiate yourself inside yourself.
Good question. I have to ask. I don't know. So next week, the colleagues of CISC who program basically this framework, they will join. And this would be, I think, a good question for them. If this recursive check is in there. I'm not quite sure.
Also, what happens if, say, you have like tasks that depend on the run output of other tasks, right? So if a task depends on the run output of another task, then that would be like subgenerator B inside generator A, right? So generator A depends on the output of generator B. So what if you have, say, generator D that also depends on the same output of subgenerator B? Do you have like yet another folder inside generator B that's as subgenerator B?
Yes.
Okay.
If I understood correctly. So basically this tree structure that we have seen before, this is represented here in the directory. Right, so maybe I can show this tree again here, for example. Right, so this would be also kind of our directory structure. We have one top, and maybe we could instead of task C, we could or task F, we could also put maybe task C.
Yeah, so,
right, so we would have now different directories, also two times the
so there's like two directories that had task C.
Exactly.
But they have the same log.
This is how, no, they have two different log files.
The two task Cs have two different log files.
Yes, I think, because for each run, basically, you have a log file. And if you maybe have here one specific parameter or they have different input parameters, the log files could be different, right?
Yeah. But like if they have the same input parameter, the caching system will then start that, right?
Exactly. And then also a good question, if now they are cached, I'm not quite sure what happens to the directories. I will check it. We can test it, yeah.
What happens if we only have a change in task B, the top level?
Yeah.
So now the second run will be finished very, very more faster than the old one. We change only the one level.
Yes. So yeah, you will gain some speed improvements if the maybe up here, everything is now cached.
So even with a real example, for example, ABC. So if you run or make layout for complete ABC and only you have a problem with top level, so second run will be finished very, very fast because all the, as a real example.
Yes, it of course depends a little bit how you integrate now, for example, the XBase or Lego 2 inside of it. If you have it like the entire layout generator is just one task, then of course you have to generate everything again. But you could make it in a maybe more integrated way that each maybe sub layout could be maybe also a task. This would require much more change, I guess, in the Lego too. But you could do it, and then you have also this caching, and then the layout generation would be really fast. Yeah. Okay.
Lego and Magic. Well, Magic has these .mag files that can be used for another integration of another mag file. So it's not need to compile everything.
Okay, so they have already their own so Magic.
Their own caching.
They have their own caching system already. Yeah. Yeah. Okay. Yeah. Sure. I mean, they probably have thought of something like that. Yeah. Yeah. Okay, so this is the logging. How do you use it? Well, you just have a self.log, and that's it. And you can just use it in the run method. So to conclude, every task has its own log file. Cache logs. This I have not mentioned yet, but if you have a cached task, later in the output you see this keyboard cached in there. So it will also be printed and reproduced basically the log file content of your first run, but it will be marked with cached so that you see, okay, this is not really run in real time. It's just reusing it, and just for info, it displays the cache, the cache log. And later on, the logs are saved in a hierarchical manner. Okay, you are now experts. Congratulations. This would conclude the part 2, the workshop. Do you have now questions again? Do anything about it? Also on the phone, if you can hear us.
You would always have to specify seeds, right? Or if you say call a simulator tool inside the task, you would always have to specify the seed there, because if say your circuit is kind of probabilistic every time, it's going to always, but it's never going to hash.
Yes, so if you have like non-deterministic tasks, I would say they are not really a good example for a cacheable task. So you would always run them and just not use the cache, I would say. Because if the result changes randomly. Oh.
The question was related with the pure functions and that kind of stuff. The entry, the parameters, they specify, and the function specify the output. So
yes,
there's no external thing that affects.
Exactly. So this is exactly the point that we also have, for example, the assets in there or something like that, that you really have all dependencies defined up front, so that the caching mechanism can check all of these dependencies if the parameters are valid, if the assets are still have the correct MD5 hash, and these things. And if anything of those changes, then we know the result should change. But if there's some randomness in there, I think there's no way to hash a random result.
Have you ever used this up to like the really end of the design process, like PPT?
This framework, no, not yet. So we just, let's say, got now this demonstrator ready, just the time for this bootcamp. And the hope, of course, is that now in this bootcamp, we maybe fill it with live and add in Lego 2. I have some ideas, I think, written down in the end, what we could do maybe with it. Yeah, but the plan definitely is to integrate all of these components, this entire flow in there. Yes.
So if we want to integrate some generator, we have to take every class and follow the structure and make the method or that kind of things.
Yeah, I would say there are these two approaches how you can integrate some new framework or whatever. The first one would be like you leave the framework as is and you just make a small wrapper around it that you can call it with some parameters and you get some result. Or you really go make a deep dive and adjust basically how it's internally working to this structure. So yeah, like going really down and say, yeah, when you create a sub layout, maybe just a transistor matrix, this is already a task. You could do this, but this is of course much more work. And you have to really know the framework because you do fundamental changes to it.
The caching part is just like a checkpoint, but cannot go back to the previous run. Let's say, for example, I was experimenting with something, then it changed the inputs, and I didn't like it. I can't go back to them.
So the cache is not removed basically. So if you change from the next run the parameters back to the old parameters, you have the cache, right? So that's why
the time execution should be the same time, because at least we need some time to check if the input is changed or not, or we have already the cache saved or not. So this time calculation should be calculated, right?
Yes, this every time it's calculated. Yeah.
But you mean the execution time should be less than the first time?
Yes.
So there really is a concern for running out of memory, right? Because say if you were doing a grid search on some parameters over one task, then all of those would be cached.
Yeah, currently yes. You can of course always mark this task as not cacheable.
Not cacheable.
Of course, but yeah, maybe. Again, I will check with our colleagues if there is some size limit on the cache. Because yeah, if you run, I don't know, 10,000 simulations to train some neural network, yeah, it could be that memory gets in your way. Yeah.
Oh, also, sorry.
Can you select layout generation engine using a single generator code? I mean,
I wouldn't say so currently. I think this is quite ambitious that you can just say, yeah, I write a layout generator with this code base and I can just use different engines for this. But not sure. Maybe, at least with back, we have the idea maybe to put below the key layout, for example, right? So this you could do, but this is maybe not really a topic of the MOSAIC framework, but more on the really lowest hierarchy level where the rectangles are drawn. Yeah. So here we have this task concept, right? You could maybe then write a back layout generator and a layout generator with some other layout engine, and then maybe exchange those if they have the same input parameters.
So currently, what tool wrappers do you? Sorry, So currently, we have tool wrappers for.
In this demonstrator, currently just for Virtuoso. No, not yet. No Spectre yet.
If it was an example.
Yeah, I put it on the left side, but it's still open. Just for Virtuoso. But yeah.
There's a dependency with back. MOSAIC?
No. So MOSAIC has no dependency whatsoever, only on this semantic version library to check the version. I think this is the only dependency currently. So it's a really generic framework and can be used for any other framework. Yeah.
I think that MOSAIC, the idea is very, it can be used with anything.
Exactly. I mean, there are
Whatever in either AEA tools, like music, for example, you can use.
Yeah, it's really generic. I mean, we came to this idea basically when we had to look what's already available. You may have heard of Prefect or some other data orchestration tools, frameworks in Python. There are a couple out there, but here we really want to, tailor it to this IP design tests.
Yeah, if I may add something, I believe it is very important. So far we have been having some frameworks that have been developed by basically IC designers that were good programmers, but actually they were not per se software developers. So this is coming, from the other side. Software developers developed it based on the inputs from the IC designers and ADA tool, let's say, engineers, such that we have good examples of scripting and how, things needs to be done. So in my opinion, this is also very, very important that we have not only a seed, but also a good example of the software developer development practice. Thanks.
This is fine. So, So what I now want to show you is the demonstrator that I prepared here. So we have this image again, this little nice house. And on top of it, I now create the schematic generator, the tool for Virtuoso, a very tiny PDK setup for the CDS FFmpeg. And on top, very basic example generator. So now let's quickly go through all of those because there's a little bit to tell you here. So let's start with the Virtuoso DF2 bridge, because here we now also open source our internal, previously internal version of the skill bridge. You may have heard of the skill bridge before.
Some of the baggies.
Yeah, Back has actually had its own implementation there. But there is this open source package that is quite heavily being used, I would say. And it creates this link between Python and Skill and Virtuoso. So running on the Virtuoso side, the server is running. This we kind of kept already here. It does some IPC communication with a Python server there. And on the other side, we have Python, and we can just call through the API any skill function. And we now extended this a little bit so that we can also have the C++ interface, a Perl API, that we have a session manager, because at least in Infineon, we have a lot of computing machines, and we may want to communicate across the network. And therefore, we also need some authentication. Previously, you could basically connect to any machine on the server farm and just execute some skill code. This is, of course, a no-go here. And therefore, we wrote an extension, and we called it now DF2 Bridge. And at its core, it has a C++ core. And it's using Swig, if you have heard of it, to generate basically this interface to other programming languages. So currently we only have Python here installed, but in principle you could also then generate code for Octave, for MATLAB, for JavaScript, for whatever language. It's quite universal. So what have we improved here? So we added authentication. We improved the session management so that we can handle multiple hosts and we can filter for the sessions that we are interested in. Then in the skill bridge, you don't know it, but there they actually changed the function names from camel case to snake case. And this is quite confusing to do this translation all the time in your head when you write the Python code. Therefore, we kept the original cadence naming scheme. Then we added the C++ core. We improved the logging. And this is not yet in this open source version, but will be added soon. Also a reverse communication, so that when you have maybe a menu item, that you then also can call the Python again, and vice versa. So that you have this two-way communication. How do you use it? Once it would be on PyPy or something like that. It's not yet there. It's just in our GitLab. You can just install it and then just say, yeah, for example, from the TrueBridge, import the Virtuoso Session Manager. You create an instance of it. And then you have the choice either to create a new Virtuoso workspace, meaning it will launch Virtuoso with all the settings already there, that it starts the server on the Virtuoso side, and will return you this workspace object. And later on, you can just call with .skill any skill function or variable. You can access everything basically in there. And the other way, of course, if you have already Virtuoso running, you can just connect to it here with this get workspace. It offers a lot more functionality in this Virtuoso Session Manager for searching and stuff like that. But this is, I think, all you need to know. Later on in the framework, you can just access this skill field, let's say. And after that, with dot, you can call skill functions. So this is already nicely integrated.
Skill, it's a Python thing that does interact with Virtuoso.
Skill is the programming language of Cadence.
Yeah.
So Virtuoso, everything the user can program there, you use Skill for that. And you can automate your design with it and do a lot of stuff. Exactly. Yeah, this should be the first question to ask. That's a good one. Thanks. Okay, yeah, PDK. Let's have a look there. We just have, again, just one view in here for the schematic generator. So I call it the anagen_tech. And it's basically a Python class. Has the benefits that, I can also generate automatic things documentation for it and stuff like that. It's quite nice. Nothing really to show here. It's just a Python file. I think I have here this extract, this snippet here. Looks like that. In that file, we just have one class, a few of class members where we just define what we see in there, and maybe some devices, MOSFETs, just added there in such a way. The nice thing again with using Python for defining this class is that we can automatically generate a things documentation with some nice comments. We can inherit stuff. So if you maybe have a technology and some derivatives out of it, you can just inherit everything and just add the changes to it. So can do incremental changes. And because the programming language, you can also define lambdas or callbacks or something like that, which is actually required for some things.
So that was the view wrapper, right?
No, this is not the view wrapper. The view. This is basically the
view.
The view. The view contains the path basically, and the path points to this file.
So this is like what's shown to be inside CDS.
Exactly. Exactly. This is then the information really. For example, in the back framework we have this tech params file. I think I would see it something like that. This could also be a YAML file.
So if it's missing, we have to make it right.
Sorry?
So if it's missing, we have to make it.
Exactly. This would, for each technology, you would have to write this one.
Yep.
Yes. Okay, now just one quick slide on the schematic generator, because here we moved away from the back primitives, which caused some problems. And here we propose basically a very simple schematic generator that takes the template in that is already available in the target technology, so that we just have to change basically based on the CDF parameters, if you know what I'm talking about, the values, the parameters of the devices and stuff like that. So meaning that the schematic generator just gets as an input some dimensions, and it will output then the OA cell view that it has been generated. So yeah, these templates, as I said, they are considered as assets. So read-only, they are provided once. And yeah, the code that you write in here, this will just modify these templates, add some dummy devices, some new topological changes, maybe even whatever you want to do in there. So why another schematic generator, just as a motivation? Because this was quite some discussion, let's say, internally here. And the first point is operating points. When I worked with the back prim devices, if you know the concept, so they have the wrappers around the technology transistors or devices, right? So that you see on top, usually it was a schematic P cell, and you can change the parameters in there, and it will give down the hierarchy to the technology, then these parameters. But on the top level, you don't see the schematic, the operating points. You always have to dive into these wrappers to see them. And this is, at least for the designing part, makes it a little bit tedious. Next, we all, or at least at Opinion, we have quite some interest, of course, and they already have a design, and they now want to make a generator out of it. And here it's quite nice because they can just start with the schematic they have, can say, okay, I would take this as a template, and I just do the modification on this thing. So nothing to redraw in here. Then, of course, it's compatible with our flows. Schematic P cells and backprim, caused some problems in our tool chains. Then we have, because we use now the skill bridge, we have this nice interactive communication. We can really do a breakpoint in the task. Maybe on the debug shell, we can change the sizes, we can duplicate things, and we see the results immediately on the schematic. So this is also quite nice. Then here we use, because I programmed this from scratch, so to say, I completely integrated it in the MOSAIC framework. So this is kind of the second approach. You could integrate something, but really reuse the entire infrastructure of the MOSAIC framework. And because now we have also at Infineon's quite some, let's say, high power technologies, high voltage. They have special devices that cannot be generalized so much. So we will have in the generators at some point special devices for the technology. And here we just have the possibility, at least we enable the possibility that they can handle those. It's maybe not then technology independent anymore, but at least they have the chance to scope with those nicely here. And one thing you may ask yourself already, what if we want now to migrate from one technology to another one? Of course, we would have to redraw the schematic templates. And here we are currently using a tool for this that does this migration automatically. So it's still a little bit of manual effort, but it's okay, I guess. Okay, and then the example generator, I will just tell you basically two things. The first one is how it's working. It's similar to back, I would say, but here you have also this command line script. So you can just say, okay, I want now an existing OA cell view or OA library to be or that we want to generate Python code out of this OA library. And this command line tool will just do it. You give it the lib. You can give it the cell and a view and an output directory, and then it will just render all of these files, basically all the tasks for each of these cells, and also a test for each of these cells. So that you can then later on just run PyTest, for example, to generate or implement all of these cells. And it's now also putting here the lib already then as an asset in here, and it will create you the basic setup for a pip package currently. So in theory, you should be able just to run pip install on this directory, and you will have it available. Exactly. So this I prepared now, basically in sub-project in the SDF environment of yours. So you can just enter this project, and everything should be set up for you. You just have, when you enter it the first time, enter your username and password to the GitLab. And don't enter it wrong. And then it should be there, everything in your project home directory. So that you can just enter this example generator, for example, run PyTest and see if you get all green errors, bugs. Carsten helped me to set it up yesterday, so I hope it runs flawlessly. Okay, so now just quick ideas or short ideas on what we could do maybe, if you are interested. One thing, of course, would be something like the GUI. Not sure it's not that important, I guess, in the beginning, but this would be also interesting, maybe with some nice virtuoso integration. So next week, on Monday, we will have this presentation of Curtis, I think, right?
Yes.
And he will present his virtuoso integration, and maybe we can reuse some things here. This would be, I think, really nice. Also, the second idea is always in my head, but I think it would be nice to think about how do we want to deploy those things. Could think of some repository where we can manage all of these different generators and upload them. And I think this is maybe the most interesting ones, that we can integrate additional frameworks and topics of yours, like, I don't know, Back, XSpace, Lego. We could add maybe key layer generators in there. Or also with the simulation part, that we maybe have some nice test bench generator, simulator tool wrappers. This would be also very interesting. Then, of course, DRC, LVS, PAX, this would be like a batch tool that we could then just call something like that. Or this is also nice if we have an optimizer in there. We could think of, we could just give this optimizer a task, maybe some starting parameters, some objectives, constraints, and make some framework for these optimizers. Would be interesting. Other topic is an idea for the documentation. What about the IP documentation or generator code documentation? This is also very important and has to be worked on eventually. And of course, if you have any other topic, it would be great if you jump on the train. Now, that being said, thank you.
You mean by documentation also to be extracted automatically, so no need to prepare it?
Could be. I mean, it could be maybe. Could be maybe the documentation. Could be maybe part of the verification add-ons.
Solution results.
So that maybe in a standard format you always get the simulation results. You could also say maybe, even more generic, if you have a task that you can, of course, generate maybe some code documentation automatically out of the doc strings, and maybe some user documentation if it just reads the parameters and the descriptions, and maybe does some nice data sheets or whatever that means for a task. Yeah, everything possible. The idea was if anything is missing in the framework or is not working or anything like that, we can just use the GitLab issues to post there an issue, and then our colleagues of SYS then can communicate or can work on it, and we have everything then listed there. I think this would be great. Then I say thank you very much.
Thank you.
Okay, I assume this is the end.
This is the end now.
I'm wrong. Okay, I will stop recording, and thank you for everybody.
Thank you very much.